All right, so it is my pleasure today to introduce Professor Ruobing Dong. Ruobing got his PhD from Princeton University, after which he was a Hubble Fellow at Berkeley, and then went to University of Arizona as a Bach Fellow before starting as an assistant professor at University of Victoria. Ruobing is an expert in modeling protoplanetary disks and planet disk interactions, including modeling what we should see observationally in such systems. And I think that's what he's going to tell us a little bit about today. So I'll hand it over to you.
Thank you very much. So yeah, happy to be here. So I took this photo the other day, and at this particular moment in the sky, we know there is a plane, even if we cannot directly see it. The tail left behind by the plane betrays its presence. The tail not only tells us where the plane was, but it also help us to characterize the plane, like it tells us where the plane has been and where the plane was going. So today I'm going to tell a story somewhat similar to this, but instead of looking for planes in the sky, we'll be looking for and characterizing planets forming in protoplanetary disks based on the structures. They can't hear me. No worries. Based on the structures planets produced in protoplanetary disks. So this animation will give us a basic idea of how stars and planets form. So we think stars form in molecular clouds as they collapse under their own gravity. We're flying to the center of a cloud, and at the center we see a newly born star. And in just a minute, we'll see a planet forming in a flattened rotating disk around the newborn star. They're also just going on in the direction perpendicular to it. We don't need to worry about it. There's a disk because when the star forms, it tries to pull material from the ambient environment, but those material have angular momentum, and they have to conserve angular momentum, so they cannot directly land on the stellar surface. Instead, they land on a big disk. This disk is called a protoplanetary disk. It is the birthplace of planet. It is made of both gas and dust particles, and it can typically last for a few million years. Now we're flying into the disk in the middle of this gaseous and dusty environment. We see a young planet just forming. The sky actually has its own tiny accretion disk around itself, what we call circumplanetary disks. This is where we think some of the moons may be forming. Actually, maybe I'll lower the light a little bit more because I think it's not. Thanks, it's a lot better. Okay. I think one thing I want to highlight or emphasize about planet formation is its planet formation is fast. So the solar system today, as we know, is about 4.5 billion years old, and the sun is just an ordinary star in the Milky Way. Protoplanetary disks, on the other hand, only last for a few million years. At the end, the gas in the dust in the disk dissipates, leaving behind a debris system. So that is to say, for ordinary star like the sun in the Milky Way, its most of its planet formation processes needs to happen in the initial 0.1% of its lifetime. If we make an analogy, if we say the solar system today is a middle-aged person, 40 years old, then the planet formation process needs to occur in the first 15 days of her lifetime. Because planets form in protoplanetary disks, we might think the best way to study how they form in observations is to directly watch them forming in disks. If we can do that, we will be able to directly constrain fundamental parameters in planet formation, such as the time scale, the location, and the local environment of planet formation. But finding planets forming in disks is difficult. Now you may be confused and you may say, wait a minute, I've heard thousands of exoplanets have been found. So how can finding planets still difficult? Indeed, many exoplanets have been discovered. Here is a diagram showing the number of planet detections as a function of time, color-coded by detection methods. These days, every year, people are discovering hundreds or even thousands of planets. But clearly, most planets were discovered using just two techniques, the red technique and the green technique, and they're radial velocity and transit observation. Both techniques, by design, strongly prefer quiet and stable stars because only those stars allow us to disentangle the tiny signal induced by the planet from the observation of the stars. Young stars, a few million years old, still surrounded by a disk, tend to be active. So they're not good target for these two techniques. As a result, almost all exoplanets found to date are orbiting billion years old sun-like stars, and only a handful of planets have been found that are still forming in disks. Due to this difficulties, we have to invent alternative strategies. In the past few years, we have come up with a new technique to find and characterize planets forming disks based on their structures, based on the structures planet-induced in disks. So the idea is very simple. So planets are gravitational perturbers. In disks, they can perturb material distribution and produce structures. We call this process gravitational disk-planet interaction. Here, I'm going to show you a movie that will show how the process looks like. This movie is produced from a hydrodynamic simulation. It will show the surface density evolution of a disk perturbed by a 1 Jupiter mass planet. This disk has a viscosity, alpha is 10 to the minus 3, and we're going to be in the reference frame co-rotating with the planet, so it won't move. So let's start. The planet launches those density waves, spiral density waves, and then it removes material from a curvature region to open a gap. And as time goes, the inner and outer gap edge become unstable, and the consequence of that is the formation of two large-scale asymmetric structures. They also go around the star. Now, the planet is tiny and faint next to the bright star and the big disk. But those planet-induced structures are on much larger physical scale and a lot more prominent than the planet itself. Therefore, if we can detect those structures in observations and convince ourselves they are produced by planets forming in disks that we cannot directly see, those structures can be the signpost of planet formation. Now let's ask a basic zeroth order question. What kind of observations do we need in order to see stuff like this in a real observation? We can address this from back of the envelope quick estimates. So first of all, protoplanets are located in star-forming regions, and the nearby ones are at a distance about 140 parsec away from us. The location of planet formation is not exactly clear, but let's say we can use our solar system as a reference. The outermost planet in the solar system, Neptune, is at 30 AU away from the star. So let's say 30 AU is a characteristic scale of planet formation. The size of those planet-induced structures, like the length of the spiral arms and the width of the gaps, is usually a fraction of the orbital separation of the planet. So for a planet at 30 AU, let's say we're talking about a few to 10 AU, give or take. 1 AU at 140 parsec is 7 arcseconds. Therefore, to observe planet-induced structures in a nearby disk on the solar system scale, we need to satisfy two conditions. So first, we need an inner working angle no bigger than 0.2 arcsecond. This is to say we need to be sensitive to what's going on close to the star. And then we need an angular resolution a few tens milliarcsecond. This is in order to resolve the structure. This angle here is very small. It's about the size of a toonie if we put it in Kingston and try to look at it from here. Regarding the first condition, an analogy that we often make is this is like how to find a firefly next to a bright lighthouse. We have to turn off the lighthouse first to see the faint firefly. So in disk observations, the equivalent would be we need to suppress light from the central star in order to see the faint disk structure very close to the star. This is, of course, only needed if we're working at a wavelength at which the star is very bright. So in the next few slides, I'm going to show you two examples to highlight the cutting edge capabilities in disk observations. In each example, I'm going to show you first a pre-2010 old observation, and then I'm going to show you a post-2010 new observations. So here is a Hubble Space Telescope image of a disk around a star called TW Hydra. It is at H-band, so 1.6 micron near infrared. The observation is in total intensity and was taken in 2005. At this short wavelength, we're looking at starlight being scattered by small dust, micron-sized or smaller in the disk. In the disk, we see a gap at 8 AU away from the star, the scale bars here. The primary difficulty in imaging disks at those short wavelengths is how do you suppress light from the central star? HST does so by putting those wedge-shaped chronograph in front of the star to block its light. Because of this, and also our inability to perfectly subtract stellar contamination from the inner region, the inner 50 AU or so is not quite accessible in this case. So if we put the solar system to scale here, the entire solar system will be within this inner hand. Now let's see how this disk look like in today's observation. So here is a new observation of the same disk on the same scale at the same wavelength by an instrument called Sphere on VLT. We can see the difference here. The new observation was taken 10 years later. This one employs a new observing technique called polarization differential imaging technique. So the image is in polarized light. And the reason for that is very simple. Direct starlight is really not polarized, but scatter light from disk is highly polarized. So if you only keep polarized light photons, you can easily get rid of the starlight but retain the signal from the disk. By doing so, the inner angle is pushed all the way from 50 AU to 5 AU. We not only see the outer gap at 8 AU with better signal noise ratio, but we also find a second gap at 20 AU, not quite accessible to HSD in the previous case. Here's our second example at a different wavelength, 1,000 times longer. This is a SMA sub-millimeter array observation of the TW Hydra disk at 0.87 millimeter. This was taken in 2008. This is a continuous observation, therefore it traces the distribution of sub-millimeter sized particles. The beam size indicated here tells us the angular resolution of the observation. So the entire disk is resolved by something like 2 resolution elements. So you see 2 emission columns. The northern one is brighter than the southern one. That tells us there's a certain degree of asymmetry in the disk, which is very useful. But with a low resolution image like this, there isn't too much else we can say. Again, let's now see how this disk looks like today. So here is an ATACMA large millimeter array ALMA observation of the same disk at the same wavelength on the same scale. You can see the difference here. So ALMA is a new radio interferometer. It has brought us a number of advances in disk observation, and perhaps the most significant one is it gives us a angular resolution and order of magnitude better. This is as if we had a pair of glasses. We now see, aha, this disk actually has a cavity at the center. It has a broad outer disk composed of a few rings, and then on top of that, we see 2 emission columns. That means some millimeter sized dust are concentrated in those regions. All these turns out to be signposts of giant planet formation, as we will see later. All right, TW Hydra and MWC 758 are just 2 examples of resolved disk observations. By now, hundreds of disks have been imaged with sufficiently small inner working angle and sufficiently high angular resolution to review structures. And most of them do show some kind of structures. Here, I'm showing you a few galleries. Now, this field is This field is very young in the sense that none of those images are possible even 10 years ago. All of them are taken with instruments that are commissioned in the past 10 years also. But at the same time, this field is booming right now. So our previous Benting fellow, Ninka Vanamara, made this very interesting plot. I think it's very interesting. So it shows the fraction of papers on protoplanetary disk and planet formation among all ADS astronomy papers as a function of time in the past 20 years. 30 years. So before 2000, the number was hovering at a low level, a fraction of a percent. This is probably mostly theoretical works. And then since 2000, the number took off, and we're looking at a 10-fold explosion in the past 2 decades. This is largely driven by observation, and particularly resolved observation of disks. Today, roughly 1 in every 30 papers in astronomy is on planet formation and protoplanetary disks. All right, lots of disk images, lots of structures. The big question is, are they produced by planets? To address this question, let's first study how theoretically what we expect planet-induced structures will look like in observations. If we can do that, then we can compare theoretical expectations with observations to see whether they're consistent. If they are, at least we will be able to say those observed structures may be produced by planets. So in the simplest setting, if we have one planet on a circular and coplanar orbit, we expect at least three types of structures: density structures, kinematic structures, and temperature structures. In the next few slides, I will explain each one of them. So, so first, density structures. From this simulation, we've seen a planet can drive spiral arms, open a gap, and trigger the formation of mutual asymmetric structures. In the next slides, I'm going to show you a disk with all three kinds of structures and how they may be possibly explained by giant planets. So here are three images of the same disk on the same scale, but at different wavelengths. The first one is a VLT sphere scatter light, near-infrared scatter light image at 1 micron. It shows two spiral arms in a near symmetric configuration at tens of EU. The middle panel is the ALMA 1 millimeter image. We have already seen it: a cavity, a broad outer disk, and two emission clouds. The right panel shows the 1 centimeter Jansky very large array JVLE image, which traces the distribution of roughly centimeter-sized particles. So you see, the interesting thing is the northern ALMA cloud has a centimeter emission counterpart, but the southern one doesn't. This emission source at the center of the JVLE image coincide with the location of the star. So how do we explain all these with planets? The three panel at the bottom shows synthetic images of the same kind. They're produced from simulations of disk-planet interactions, and they tell us theoretically what we expect planet-induced structures should look like at various wavelengths. So the first panel shows if we have a giant planet multi-Jupiter mass on the outside of the disk, it can drive a pair of grand design arms inside its orbit in scatter light, much like what we see here. The same planets open a deep gap and trigger an instability called the Rossby instability at the inner gap edge. The outcome of the instability is a formation of a large vortex. A vortex works like a giant vacuum machine in the disk, and it sucks dust particles to its center, which is why we see a millimeter emission cloud at millimeter wavelengths, because there are tons of millimeter-sized particles here. A second giant planet is invoked at 35 AU to open another gap and trigger the formation of a second vortex at the outer gap edge. This one also traps sub-millimeter-sized particles and reproduces the sub-emission cloud seen by ALMA. However, only the northern vortex is good at collecting centimeter-sized particles, which is why it has a centimeter emission cloud counterparts. The southern vortex is already in the process of decaying, so it doesn't trap centimeter-sized particles as well, which is why we don't have a counterpart in JVLE observations. All right, in addition to producing density structure, a planet can also perturb gas and make them do non-Keplerian rotation. And this is what we're going to discuss next. So here are two schematic view of a disk. Top one is a face-on view, and the bottom one is agile. In a laminar disk with no planet, what the gas does is very simple. The gas just do Keplerian orbits around the star, right? Very simple. And there's almost no motion in the radial and vertical direction except random thermal motion, of course. Now, let's say a giant planet forming the disk. This planet will perturb gas motion in a few different ways. So first, the planet may assemble a circumplanetary disk around itself. This mini disk goes around the planet instead of the star. And then the planet may launch density waves. And when gas crosses those density waves, their orbits will be perturbed. And finally, if a planet can open a gap, then it is expected to drive something called a meridian circulation around the gap, especially at the gap edge in this format. We'll come back to this later in the talk. So once the planet forms, we're going to see all these, or at least we expect to see all these red motions that are not Keplerian motion. If we can detect them, they can be the signpost of planet in the disk. So here is a real-life example showing the detection of non-Keplerian motion and how possibly that could be explained by planet. The left panel here shows a, this is called a channel map, shows a CO emission from HD 163296 at a line of sight velocity of 1.2 kilometers per second. So long story short, we can think of this as a map tracing the distribution of gas that is doing a line of sight motion at 1.2 kilometer per second. So at this very location, the gas emission shows a little what they call kink structure. The middle panel zooms in on this region, and here the black dashed line shows the expected contour of gas emission if the gas is doing Keplerian rotation, and the white curve shows the contour of the actual emission. Without going into any of the details, you can see the dashed curve is different from the white curve, right? So that means the gas here is not doing Keplerian motion. The rightmost panel shows such a motion can be explained by planet. So this is a synthetic CO channel map. And in this case, a giant planet is placed right here, and it can drive this little kink shaped structure to explain the observations. All right, finally, let's talk about temperature structures. Planet, so here is an example. How does a planet drive spiral-shaped temperature perturbation? The story is very, very simple. So here is a gas surface density perturbation. Here's a planet that drives this density wave. The spine of the density wave has a density higher than the background disk. This is why it is called a density wave. And therefore, it has a higher pressure. So when gas move into the density waves, they get compressed. As long as the disk is not isothermal, gas get compressed, they're heated up. And then when they leave the density waves, they get decompressed and their temperature drops. This middle panel here shows the corresponding simulated gas temperature perturbation at a height of scale height above the disk midplane from the model. So it shows a planet. So why we do it at a 3 scale height? That's because 3 scale height is where we think CO emission come from. So a planet is able to drive a spiral-shaped temperature perturbation at the level of a few Kelvin, or a fraction of 10 to 20% of the local disk temperature. Such temperature perturbation may have been directly detected already. So the right panel shows a real temperature perturbation inferred from CO observation in the TW hydro disk. Indeed, in it, you see those spiral-shaped temperature, positive and negative, on the order of a few Kelvin, qualitatively quite similar to the simulations. All right, we have seen structures in disk, and we have seen some of them, at least some of them may be explainable by planets. So what can we learn about those planets from disk observation? I think there are at least 2 things we can do here. First, we can constrain the properties of planets in individual systems. And then once we have a large enough sample, we can probe the statistics of planet formation. I'll talk about the first one first. The idea, again, is very simple. As we can imagine, if a disk structure is produced by a planet, then we expect the morphology of the structure should depend on the property of the planet. If we change the planet mass or we change the planet's orbit, we expect the structures should change accordingly. And if we can quantify the relation between the two, it may give us a way to infer the property of the planet based on the observation of the disk structures. So here is an example. How do we constrain the mass of a planet that is able to open multiple gaps in a low viscosity environment? So this movie will show us the surface density evolution of millimeter-sized dust particles in a disk perturbed by a planet. This simulation has a low viscosity. Alpha is 5 times 10 to the minus 5. Again, we're going to be in a frame in which the planet doesn't move. So let's start the movie. Very quick, a southern orbit. The planet drives some density wave and very quickly opens a number of gaps. This is different from the previous simulation we see, in which only one big gap is open around the planet's orbit. This is caused by the difference in viscosity. So this one, the old simulation, has a viscosity much higher than the new simulation. In a disk, now we know a planet will drive several density waves, and when density waves dissipate, they open gaps. In a high viscosity environment, all these density waves are damped right around their launch location, and those are fairly close to each other. That's why all these gaps overlap. But in a low viscosity environment, there's no viscous dissipation, and the waves can freely propagate for a while until they're damped by other mechanisms. And in those cases, the damping location of the waves can be very different. And that's why we see multiple gaps.
Question?
Sure.
So in the low viscosity case, how can you be confident that you've converged, in the sense that a real disk would evolve for many, many, many orbital times? And when the viscosity is small, couldn't there be long-term transient behavior in the structure that the simulation doesn't have time to resolve?
This is a very valid question. Indeed, I guess to some extent, we don't have, like we're not 100, okay, like we're 100% sure the simulation hasn't reached full steady state, and it will keep evolving for a while. Qualitatively, like in this case, the dust ring patterns will remain similar for a few thousand orbit, but eventually, once the dust rings becomes narrow enough and the density of the dust in the ring reach high enough value, there could potentially be other instabilities be triggered. So to some extent, yes, this is transient phenomenon, only lasts for a certain amount of time. That said, usually these days we're talking about planets at tens of EU, so a few thousand orbit, that's still like a fraction of a million years, so not particularly short, I would say. Yeah. All right, so coming back to our simulation. So among all these gaps, let's pay attention to these two gaps. They're on the two sides of the planet orbit, and they sandwich a ring of material in between. And these two gaps themselves are sandwiched by another two rings on the inner and outer side. So in total, we're looking at a very characteristic triple ring and double gap structure. Now, if we repeat the simulation, fixing everything else, but change the planet mass, we'll see the gap system to evolve. Here are 5 simulations. They each have a planet, their planet mass increased to the right. Every planet opens a few gaps, and clearly the gap system becomes more compact once the planet mass increases. Specifically, if we pay attention to the signature double gap on the two sides of the planet orbit, we can measure the separation between the two gaps, and that's delta. And that delta can be fit by a function involving planet mass, MP, and a few other parameters that are related to the disk. Now, this fitting function provides a way to infer something we're extremely interested, the mass of the planet in a disk, from something we can easily measure, the separation between two gaps. Now let's apply this to a real system. The right panel shows the real ELMA observation of HD 169142 system. It has the very characteristic triple ring and double gap structure. Go ahead.
Yeah, when you have a viscous disk, that does typically assume that the main two torques which are working to form the gap is the balance of the gravitational force from the planet with the viscous torque from the disk. But when you have a low viscosity disk, it's not really the same thing anymore. So what's the main two torques which are leading to that equation you have there?
Right. So in this case, okay, maybe we can first go through the second case. If you have no viscosity, then indeed those gaps will keep be opening, which means I'm not sure if we will never reach a steady state, but for a very long time there no resistance from opening, so the gap will keep being open. In our case, we do still have a small viscosity, so eventually the gas gap may reach some kind of equilibrium, although we haven't reached that yet. That takes a long time. So in a real disk, it shows this triple ring double gap structure, which we form a hypothesis. Maybe it's opened by a planet whose orbit coincides with the middle ring. If that's the case, we can just take a ruler and measure the separation between those two gaps, and then plug in the equation. After assuming certain other parameters about the disk itself, we can infer the mass of the planet. It's about a 10 Jupiter mass or mini Neptune sized planet at 60 EU from the disk. Here is a radio transfer simulation of a disk model with such a planet, and indeed the planet shows the triple ring double gap structure very nicely. All right, moving on to talk about statistics. So the idea is like this. Let's say we have a sample of disks and we go out and image every one of them. When we find spar arms in some of them and gaps in the symmetry in some others. Now for every disk with structures, we can apply techniques similar to the one I just introduced to infer the property of the planet from the observed morphology, structure morphology. Once we do that to all the disks, we can form an opinion what kind of planets are forming in this sample. So let me give a more specific example. There are about 24 known single Herbig AB stars within 200 parsec from us. So Herbig stars are the progenitors of main sequence stars with a mass higher than 1.5 solar mass or so. So here is a sample. It's a volume limited sample. Now, 10 out of those disks have been imaged in scatter light. Every one of them shows some kind of structures. Specifically, 5 of them show spar arms. These 2 show a pair of grand design arms. And those 3 show multiple arms on a smaller scale. Now, previously, I've argued giant planet may explain spar arms in scatter light. Now, if we make a bold assumption to say those spar arms are produced by a giant planet, this is a very bold assumption, but let's go with it for now. Then the sample immediately gives us the following statistics. At least 5 out of 24 Herbig stars, or 20%, are forming giant planet at 10 to 100 EU. This is small number statistic, and the assumption we made is debatable that all the spar arms are made by giant planet, but it illustrates the power of disk imaging sample in constraining planet formation model. A good planet formation model should be able to explain statistics like this: why intermediate mass stars like to form giant planet at large distances. All right. We have seen structures, they may be explained by planets, and if so, they can help us do wonderful things, constrain the mass of the planet, so on and so forth. All is good, except everything builds on a big assumption. Are structures really produced by planets? As you can imagine, we think, of course, not all structures are produced by planets. Alternative hypotheses to explain structures have been explained. In most cases, at the moment, it is still unclear which mechanism is actually working. But in certain cases, we think nature has offered enough clues to make us believe the non-planetary explanation may be perhaps more likely. So here is one of such examples. So the image here shows the scatter light, near-infrared scatter light image of the circumbinary disk around the binary protostar ZCMA. So the 2 stars are very close to each other on this scale. This disk shows a very peculiar one-arm spiral. This arm has been known for a long time, but its origin is always a mystery. So we were thinking, to figure out what's going on in the system. So we went ahead and took an image of the system at 1 millimeter wavelength using ALMA, and here's the image. So we detect the counterpart of the spiral in millimeter emission, as you can see here, although only the part close to the center. And then we find a point source at almost exactly along the extension of the spiral at a distance, actually quite large distance, at 4 arcsecond away, or 4,000 EU. This source has also been detected in various gas emission, which makes us think it is associated with the system instead of a random foreground or background star. The unique configuration of the system between the spiral and the newly detected point source make us think we're likely witnessing a young stellar object that has just performed a flyby of the circumprimary disk. So here are 2 simulations of a flyby event at 2 different viewing angles. On the left, the circumprimary disk is face on, and on the right, the circumprimary disk is edge on. The flyby object is going to come from lower right corner, and the orbit of that guy is actually at 45-degree inclination with the primary disk. Although at the face on image on the left, we couldn't quite tell that. So let's play the movie. This guy comes in and perturbs the disk, and it goes away with 2 spirals. So the flyby drives 2 spirals, which looks fairly symmetric in this view, but the 2 spirals are actually quite asymmetric. as we will see in the right image, in the movie on the right hand side. So now again, the flyby comes in, perturbs the disk, and then leaves the system. See here on the right, you can see the two spiral arms are very different. The one in between the flyby object and the primary star is being lifted above the disk plane. The other arm is remaining embedded in the disk. This difference produces a key difference in illumination pattern, as the primary arm between the flyby and the primary star is much better illuminated than the secondary spiral arm, because the former, the line of sight between the spiral and the primary star is not blocked. Indeed, if we produce a synthetic scatterlight image of the model, as we see in the middle panel at the bottom, we only see one spiral arm that points to the flyby star. So this overall geometry is fairly consistent with the ZCMA observation we have, a single arm spiral pointing to an object. So this newly detected point source has been seeing a longer wavelength, centimeter wavelengths, but not a shorter wavelengths, infrared wavelengths. So we think perhaps it is a very young stellar object whose emission concentrated at short wavelengths, or it could have an edge on disk itself.
So can people still hear me, or? Okay, so the dust continuum doesn't show the same spirals as the scattered light is. Is that because the dust has decoupled from the spiral arms?
Right, that's primarily the reason. The millimeter dust spiral is shorter than the micron size dust. All right, so some disk structures are probably not produced by planets. How can we tell in a specific system which ones are produced by planets? The best way to do that is to, the best way to address that question is, of course, to look for the predictive planets. As I argued at the beginning, this is very difficult. Nevertheless, a huge amount of resources have been invested, and there are planets being detected. And the best example of them would be PDS-70 system. The two left panel shows the scatter light image and millimeter continuum observation of the disk around PDS-70. We see a large cavity, 16 U in radius. Such cavities have long been argued to be opened by multiple giant planets. So they're essentially common gaps of planets. The two middle panel shows the synthetic images of those common gaps, which look very similar to the real observations. The right panel, the background is a scatter light image, and the blue inset shows an image at H alpha wavelengths. So 2 point sources have been detected at H alpha wavelengths, and they're interpreted as accreting planet. So PDS-70 is one of those systems. They show disk structures that have been predicted to be produced by planets, and then planets have been found. The most recent ALMA observation actually detect a point source, millimeter emission point source at the location of PDS-70C, which is interpreted as a circumplanetary disk. All right, PDS-70 is very nice. However, such cases are still very rare. So that means direct test of the hypothesis is still difficult. Therefore, we have to look for indirect tests. So in the next few slides, let me show you a few examples. The first is pattern speed. That is very simple. So planets drive density waves. Very cool. Those density waves co-rotate with the planet. That means they go around the star at the same pattern speed. Therefore, if you can measure the pattern speed of spirals, you can immediately back out the semi-minute axis of the planet using Kepler's third law. Here is an image of the MWC 758 disk taken in 2015. Now, here's another image taken 4 years later. So ignore the overall change in the illumination pattern. Here's a very simple question. Do we think the spirals have rotated? So theoretically, we argue the spirals could be caused by a planet on the outside at 100 AU or so. Therefore, we're talking about 1 degree of rotation in a few years. So very small. Nevertheless, this is work done by Bingren, a postdoc at Caltech. He did careful analysis and concluded the spirals are rotating at a very tiny rate, 0.2 degree a year. This one immediately gets translated into an orbit of the planet that is qualitatively consistent with the previous models. A planet driving 2 arms inside its orbit. So spiral arms have been detected in scatter lighting over a dozen disks. We can further test the planet hypothesis by asking the following question. How do we expect planet-induced spirals to look like at other wavelengths? And if we really take images of those systems at other wavelengths, do observations agree with the theoretical expectations? So my student Jess looked into this. So she used Fargo simulation to simulate and obtain the surface density and temperature perturbation of some millimeter-sized dust particles perturbed by a planet. And with these two, she was able to simulate ALMA images. So those are theoretical predictions of how planet-induced spirals should look like at millimeter wavelengths. So she found spirals induced by giant planets are supposed to be detectable using ALMA under reasonable conditions. So we're talking about up to 10 hours of integration time. Therefore, in principle, the millimeter image of those systems, if the spirals are produced by planets, are supposed to show millimeter spirals. And then she found spirals in adiabatic disks are more prominent than the ones in isothermal disks for a very simple reason. Adiabatic disks give you an additional boost in temperature. So right now, Jess is looking at the real ALMA observations to see whether theory agree with data. So far today, I've only focused on planet-induced structures in the 2D disk plane, radial and azimuthal direction. But planet can also drive structures in the vertical direction. And if we can probe that, that will open another dimension to test the planet hypothesis. So this is the work done by my student Jiaxing B. So he looked into the vertical structure of dust particles perturbed by a planet. So here is a giant planet, it opens a gap. This is a schematic plot on the left. So inside the gap, the planet drives meridian circulation. So planet pushes gas away from its orbit along the disk midplane. And then at the gap edge, the gas rises to the disk surface before the gas comes back into the gap and falls towards the midplane close to the planet. That's what the meridian circulation is. Meridian circulation technically is only in the gas, but if dust is reasonably well coupled with the gas, meridian circulation can also drag dust together. The right panel shows a meridian cut of the dust density distribution. If there's no turbulence and no planets, then all the dust particles, all the large dust particles are expected to settle to a thin layer at the disk midplane. Now, if there is a planet, however, the planet would drive those meridian circulation and they can puff up the dust at the gap edge. That means those dust rings are supposed to have a finite thickness, and those finite vertical structure may be observable in observations. So here is a schematic view of a dust ring at face on. Now let's tilt it. If the dust ring has infinite small thickness, so in one plane, then if you tilt it, it will just be compressed along the minor axis. But if the dust ring has finite thickness, something like a donut, then an additional geometric effect will kick in. Now, assuming the ring is optically thin, then the line of sight penetrating the two ends along the major axis will go through a thicker layer of dust. Then the line of sight going through the minor axis. This is a little geometric effect. This will result in the following effect. This is a simulated ALMA observation. The two ends along the major axis will be brighter than the rest of the ring. Such a phenomenon may have already been detected. The right two panels shows real ALMA image of the disk HD163296, which shows a bunch of rings. The two panels are showing the same data except with different stretch. So the middle ring in this particular disk shows this signature. The ring is brighter along at the two ends along the major axis than the rest of the disk. It indicates a finite thickness of the ring, and perhaps they're produced by planets inside those gaps. All right, that's the main part of my talk. I've showed how to find and characterize planets forming in disks based on their induced structures, much like how we find planes in the sky sometimes. So in the remaining 3 or 5 minutes or so, I want to show you something, a new direction that we're exploring, how to use machine learning or neural networks to help us study simulations. So we need simulations, lots of them actually, because in astronomy, we don't have the luxury to be able to do physical experiments. So numeric simulation provides a nice alternative. Nevertheless, simulations are computing intensive and they take a lot of human resources. So I've been thinking whether it is possible to use neural networks to help us speed up the simulation or even replace the simulation altogether. You know, among other things, that saves a lot of CO2 emission, right, out of those supercomputers. They burn a lot of powers. So in our case, we need simulations to follow the evolution of a disk and a planet system. Our system obeys physical laws, and in the simplest setting, if we're talking about 2D gas-only isothermal system, our physical laws are 3 simple equations, Navier-Stokes equation, 1 for mass conservation and 2 for angular momentum, 2 for momentum conservation. We solve them for 3 unknowns, surface density and radial velocity and azimuthal velocity. To do that, of course, we need to couple them with boundary and initial condition. That's essentially, in a nutshell, what our simulation does. So here is a super simple example. We have an axisymmetric system with no planet. The 3 panel here shows the 3 variables: surface density, radial velocity, and azimuthal velocity. Initially, most of the mass in the disk concentrate in a narrow ring. Now let's see, and the disk has viscosity, so we'll see evolution driven by viscous diffusion. There's no planet. So let's see how the disk evolved. As you would expect, viscous diffusion makes the ring wider and its peak amplitude drops, right? That's a smearing of the ring, very simple. But the cool thing is, these movies are not produced by a simulation. They're outputs from a neural network. This is done by my graduate student, Shenyuan Mao. And in addition, the training of the neural network does not involve training set. So this is not like we run thousands of simulations first, and then we ask the neural network to learn from this. Instead, in this case, we try to teach the neural network physics. So whenever the neural network produces an outcome, we ask the neural network, do you think your solution obeys physical laws? That means if you plug your solution into those 3 equations, do you get 0 on the right-hand side? If you don't get 0 on the right-hand side, that means your solution does not obey physical laws. So effectively, those Navier-Stokes equation becomes a loss function of our neural network. Initially, of course, the right-hand side are not 0, they're very large. And then the neural network use a variety of backpropagation and gradient descent techniques to lower the right-hand side. And eventually, when the right-hand side are sufficiently close to 0, we claim we have reached a good approximation of the correct solution. So let's see how the neural network performs. Here at the bottom, we're going to compare the output of the neural network, which will be the blue curves with, which will be the orange curves with the output from a hydrodynamic simulation, which are the blue curves. We take the hydrodynamic simulation as a ground truth. And the difference between the two will be the absolute error of our neural network. And the three panel at the bottom shows a radial profile of the 3 quantities. So let's start the movie here. You know, the ring drops and it becomes wider, driven by viscous diffusion. Very simple physics. So in surface density, our neural network get an absolute error on the order of 1%, so not too bad. For radial velocity, it's an order of magnitude bigger. The errors are now 10%. For azimuthal velocity, the errors are tiny. You don't even get to see on this scale. What does this even mean? So the 0th order physics in this very simple system is not viscous diffusion, actually. It's Keplerian rotation around the star. That's a 0th order physics. The rightmost bottom panel shows our neural network perfectly, almost perfectly captures that physics. It gets gravity and Newton's law almost exactly right. However, on the other hand, the first 2 panels shows the evolution of the ring in density space and the associated radial velocity are not captured correctly, or at least not as good as we hope. That means the neural network still has some trouble learning those first order physics. The viscous stress is, of course, a lot smaller than gravity. So that's what we get so far. This is pretty much still working going, but just wanted to share with you a new direction that we're up to. Thank you very much.
We have time for questions. I'll go with, okay, I'll bring the mic to you, hold on. What's for the people? Okay.
I'm just curious about the giant spiral. What's the condition for your simulation?
So Yen asked, for those online, Yen asked about the two spiral and what conditions, under what conditions two spirals are created in disks. And their angles.
Right. So, you know, in the linear theory that Scott works a lot, the theory would tell you the pitch angle of the spiral doesn't depend on the mass of the planet. But in the nonlinear regime, what people found in simulation, and now there's some preliminary theory as well that shows the pitch angle of the spiral also depends on the mass of the planet. So to open those very open arms, it looks like you need massive planets. So the openness of the arms is an indication of the mass of the planet. So that's one thing. And secondly, of course, that's a Euro dependence on the sound speed in the disk. If the disk has a high sound speed or large aspect ratio, the arms will be proportionally more open. So we typically find you need mass planet, let's say. And sound speed aspect ratio, you know, like 0.07 or 0.1 or something.
So my question is,
sorry, we have a question in the chat from Taylor. For your experiments with neural networks, I assume they are faster than traditional hydro simulations. If so, how many times faster?
See, I'm very embarrassed to tell you that the training of the model of the neural network itself is actually a lot more expensive than the traditional hydro simulation. But the hope is the neural networks, once you train it, then if you change the parameter, you can quickly produce an output. A regular simulation, you know, if you change the planet mass from 1 Jupiter mass to half a Jupiter mass, you have to rerun your 3000 Fargo simulation. With the new network, the perspective is, we hope eventually it will save time, but not at the moment. We're still generating more CO2 than we should.
So my question is, I thought the occurrence rate for like Jovian planets large enough is like pretty low, something like 10%. So does that mean like we should not see like these structures very commonly in protoplanetary disks? Because I thought they were like very common in like observations.
Right, that's a very good question. So maybe I can go back to one of my gallery slides, which shows many disk images. So if you look at those images, if somebody asks, what are the most common features in proton disk image today? You would probably tell him or her, it's narrow gaps or rings. Like this one is a very typical one, and all these guys, and more often in alpha observation than in scatter light. So for dust rings and gaps in millimeter observations, the current thinking is they can be produced by relatively low mass planet, even under conventionally large viscosity. You're talking about Saturn mass planet. So on that end, we're still consistent between the direct imaging planet community and the disk modeling community. We do have some tension. For example, in the spiral case, we argued if the spirals are produced by planets, then it looks like at least 20% or probably more intermediate mass stars are generating giant planet, multi-Jupiter mass at tens of EU. This may be in some tension with observation. There are some discussion how to mitigate that. One of them says, as you can well imagine, people argue maybe the young planets are not as bright as you think. Maybe they are dark most of the time, and they also go through sort of planetary a priori cycles. So they occasionally become bright, but they're very faint most of the time. So these planets are at a very large distance. So we're talking about 50 AU, 100 EU. So there are these signal. Oh, Gaia. So for Gaia, I think Gaia, I have to check, but I saw Gaia doesn't quite go to a few tens of EU. But I guess if they're really massive, getting close to binary system, perhaps. Yeah. Don't know the exact numbers. Yeah.
The one system where you measure the pattern speed, is the spiral leading or trailing?
Very good question. They're trading, so consistency. Yeah. Otherwise, won't dare to publish the papers.
So earlier when you were showing how you can measure the size of the gap and determine the mass of a planet, you also showed that for different viscosities, the gap sizes can be different. So how do you know the viscosity in order to be able to measure the planet mass?
Very good question. My answer is we don't know. So, and that's indeed a very key part in most cases. So if we just see a random gap in a disk, like a single gap, and you ask, what is the mass of the planet producing this gap? This is a question very difficult to answer. If you force an answer, it will have a huge uncertainty because viscosity is the main contributor. But there are cases like this. This is very characteristic, 3 rings sandwich 2 gaps, and this particular system is nice because this set of features isolated from everything else. So this set of features can be explained by one planet. I think this is sort of the beauty of those occasionally nice system. And from that, maybe we can say, in order for one planet to produce this structure, we argue the viscosity needs to be low, even if we have no other strong arguments. Yeah.
Online from Peter. Peter, can you unmute and ask?
Yeah, thanks. Thanks for the very interesting talk. On the flybys that produce the one-armed spirals, is the stellar density in these star-forming systems high enough that you would expect these collisions?
Yes. So yes and no. So for that particular star-forming region, so that's a region at 1.1 kiloparsec from us. So to my knowledge, that region is not particularly well studied. So we don't have too much detailed information about that cluster in particular. But if we use typical cluster number density measurements from other clusters, the average encounter timescale between 2 stars within that distance is on the order of, let's say, 10 million years. So the encounter timescale is not too different from the age of the system.
Interesting. Thank you.
We have a question in the chat from Taylor about the different results in high versus low viscosity environments. What causes the disk to be high or low viscosity? Why are some disks more viscous than others?
Again, that's an excellent question, and I don't have an answer. As far as I know, 100 different series explaining why disks should have high viscosity or low viscosity. Yeah, I'm not sure I have a simple summary of the state, but maybe if I try, let's just say, in a laminar disk with no turbulence, then we would think the disk would have low viscosity. If any of the mechanism works to produce turbulence, then in a way, we will think that effectively produce high viscosity and affects gap opening.
Yeah, so very nice talk. So I had 2 questions. So the first is on the result of Jiaqing B, where he was showing that if you have meridianal flows, you
That's right.
puffed up dust ring.
Right.
So the gas continuum, or sorry, the gas kinematics, Richard Teague also showed for that system, also showed direct evidence of meridianal flows.
That's right.
Is Jiaqing B's continuum results consistent with that?
Right. That's a great question. We haven't tested. We're looking at the millimeter continuum, try to tell the signature from the smooth variation from the ring. But you're very right. That particular disk does have gas oscillation, and we should compare. Yeah. Right. Yeah.
Yeah, and then so it's the second one's quicker. So for Jess's result, so the fact that most disk continuum images show mainly axis symmetric structures, does that imply that the disk cooling times are likely very short because the disk has to be isothermal?
That's again something we're looking at it right now. It is initially we thought it's a little surprise, just showed they're produced by Planet. We should see their ALMA counterparts, but at the surface, it looks like they're not there. There could be a variety of explanations. Perhaps those ALMA integration time are not long enough. That's possible. We're still looking at it. And another is, as you said, perhaps disks are not as adiabatic as we think, which will make the spirals faint.
Past 4 o'clock, so we'll go ahead and end the formal or official question and answer period here, but you're more than welcome to stick around and chat informally. So let's thank Robin one more time, and